Good morning. So in this video, I'm going to discuss loss work. So loss work is defined as the difference between W ideal and W actual. So loss work, we're going to derive an equation for loss work and solve a problem using this equation. So let me share the PowerPoint. Okay. So loss work is defined as W loss is equals to WS minus W ideal. So W is the actual amount of work produced by the system. So the difference with the reversible work or the ideal work is W loss. So let's derive the equation for W loss. So right here we have the general balance equation. W plus W dot plus Q dot is equals to delta H plus delta PE plus delta KE. Okay. So when work is reversible, delta S minus Q dot divided by T surrounding is equals to 0. This means that the delta S total or SG dot is equals to 0. Now, isolating Q from the equation will give you T surrounding times delta S times M dot Fs. So replacing Q dot on our first equation will give you the equation for WS ideal as we previously derived on when we derived the W ideal equation. So we have here delta H plus delta KE plus delta PE times M dot minus T surrounding times delta S times M dot Fs. So now let's try to derive the equation for WS. Remember, W loss is W S minus W ideal. So WS is simply equal to delta H plus delta KE plus delta PE times M dot Fs minus Q dot. So combining the two equations, because the definition of W loss is WS dot minus W ideal, combining these two equations, so the first term will cancel out. The one that contains delta H, delta PE, and delta KE. So what will remain is W loss is equal to T surrounding times delta S M dot Fs minus Q dot. So, kasi diba ito yung WS. So ito yung WS, kaya siya yung naging negative Q. No? Tapos ito yung W ideal minus W ideal. Kaya yung T surrounding times delta S times M dot Fs, siya yung naging positive. So this is our equation for W loss. W loss is equal to T surrounding times delta S M dot Fs minus Q. Let's continue our derivation. Since W loss is equals to this one, we derive this from the last equation. And then we have this equation for SG. SG is equals to delta S M dot Fs minus Q dot divided by T surrounding. So we're going to combine these two. Um, so as you can see, if I'm going to multiply this with T surrounding, the second equation with T surrounding, I'm going to multiply this with T surrounding or sigma. So we're going to have T sigma times SG. This is that part, ano? Tapos T sigma times delta S times M dot times S. Tapos this one will cancel out the T sigma. You have T dot. No? Tapos, if you're going to compare the first equation, it's the first equation, equation number 1, and then equation number 2. And then we're going to isolate P sigma delta S M dot Fs on the first and second equation. Okay. So the first equation will give you W loss. When you combine these two, when you combine equation 1 and 2. And then you create T sigma delta S M dot Fs. So we're going to have W loss from the first equation plus Q dot W dot W loss dot. And then from the third equation, this is equal to this one, T sigma, T surrounding times SG dot, okay, plus Q dot. And then Q dot cancels out. So W loss is T sigma or T surrounding times SG. So this equation right here is the one we're going to use to solve the problem. So now, basically, you just multiply the S generated with T surrounding to get W loss. Okay. If you ever forget the formula for W loss, you can browse in the chapter 4 of Perry. There you can find W loss on page 39. W loss is equal to T sigma times SG. This is T surrounding times S generated. Okay, so let's try to solve example 5.9. So the two basic type of steady flow heat exchanger are characterized by their flow pattern. So we have heat exchangers. These are equipment used to increase or decrease the temperature of streams. No? So the two types are co-current and counter-current. So pag co-current, both the streams enters at the same side of the heat exchanger. So heat exchangers are generally pipes. No, they are made up of pipes and drums, or cylinders. So the pipes are placed inside the drums. So one stream flows inside the pipe and the other streams flows outside of the pipe, pero inside siyempre of the drum. So for a co-current heat exchanger, the streams flows from the same direction. So kumbaga, the entrance of one stream ay katapat nung entrance ng another stream. No? So let me illustrate that. So pag co-current, the illustration is like this one. So halimbawa, ito yung heating stream mo, ito yung cooling stream mo, ganyan yung co-current. Dito lalabas, dito rin lalabas yung isang stream. Pag naman counter-current, so pag counter-current naman, magka-opposite yung entrance ng stream. Kung dito pumapasok yung hot stream mo, dito naman lumalabas yung cold. Dito naman pumapasok yung cold stream. So magkatapat yung outlet nung cold stream at saka yung inlet nung hot stream. So ganun din sa kabilang side. So ganito yung counter-current. The two types are indicated in figure 5.9. So in co-current flow, heat is transferred from a hot stream flowing from left to right to a cold stream flowing in the same direction, as indicated by arrows. In counter-current flow, the cold stream again flowing from left to right receives heat from the hot stream flowing in the opposite direction. The line relates the temperature of the hot and cold stream, TH and TC respectively, to QC dot. The accumulated rate of heat addition to the cold stream as it progresses through the exchanger from the left end to an arbitrary downstream location. So what this sentence is trying to tell you is whatever heat is lost by the hot stream is is captured by the cold stream. Ganun lang naman yun. Generally, in solving heat exchanger problem, we assume that no heat is lost to the surrounding. No? So we're going to consider the two cases, both the co-current and the counter-current. So it's given that the hot stream enters at 400 Kelvin and it goes out at 350 Kelvin. Okay? And then the cold stream enters at 300 Kelvin, and then the flow rate of the hot stream is 1 mole per second. So the minimum temperature difference between the flowing stream is 10 K. So, siyempre, pag parallel, katulad nito, this one is parallel o concurrent. Initially, mataas yung temperature gradient. Magkaiba pa yung temperature nila, malayo pa. So sabi dito sa problem, siyempre, paglabas sa kabilang side, magkalapit na yung temperature niyan. So ang sinasabi sa problem, yung temperature approach sa parallel ay 10K. Ganun yun, Ganun yung 10K din. Assume that both stream are ideal gases with Cp is equal to 7.5 R. Find the loss work for both cases. So basically, T surrounding is 300 Kelvin. Basically, ang gagawin lang natin is we simply found Sg, tapos yung Sg, yung generated entropy, i-calculate lang natin yung yung W loss by multiplying Sg with T surrounding. So both for co-current and counter-current. Okay, so probably I'm going to share a whiteboard para mas malaking masusulatan natin kasi relatively medyo mahaba yung solution. So let's start with the parallel, Let's start with the co-current. Co-current heat exchanger. So yung pH1 natin, if I remember it right, this is equal to 400 Kelvin, Tapos paglabas niya, pH2, this is equal to 350 Kelvin. Tapos yung TC1, let me check TC1. So TC1 is 300 Kelvin. Okay. Tapos TC2, hindi given. Pero sabi sa problem, yung temperature difference daw dito sa dalawa ay 10 Kelvin. So this is 340 Kelvin. Okay. Tapos it is given that NH, yung flow rate ng hot stream ay 1 mole. So, before natin makalculate yung SG o kaya yung W loss, we still need to find NL, yung flow rate ng cold stream. So, NC, NC muna. So, para makalculate natin yun, mag-heat balance lang tayo. So, kung ano man yung amount ng heat na ma-loss ng heat ng hot stream, ma-absorb yun ng cold stream. Parang ganun lamang naman yung equation natin to find NC. So basically, it's MC, ang heat na re-release ng hot stream ay MCP delta T. Ngayon, yung CP ng cold gas, kasi di ba, i-assume natin air, Yung CP ng cold gas at saka yung CP ng hot stream, parehas lang naman. So dun sa MCP delta T, magka-cancel out lang yun, So parang ganito lang yung equation natin. Yung heat na ma-release ng hot stream, equal lamang yun dun sa heat na ma-release ng cold stream. Diba? That's logical, Tapos ito, parasang naman yung kanilang specific heat, so we can cancel this out, Actually, this is M dot, M dot, M dot to, M dot, NH. So, parang, so mas eksakto is NH, so NH dot, CP delta T ng hot ay equal sa M dot CP delta T ng cold. Sabi ko nga, kasi parehas lang naman yung kanilang heat capacity kasi kahit malamig o mainit yung air, magka-cancel out lang yung Cp. So, ang n.h ay 1 mole per second. Tapos, ang change in temperature natin is, gagawin natin positive, ano, para pala silang positive. 400 minus 350. Kung gusto niyo yung final minus initial, ibahin niyo lamang yung ano, no? Ibahin niyo lang yun. Parang dito kasi parang naging negative siya, ano? May negative to. Kasi parang nandun din sa kabilang side, tapos pinaraspose ko lang sa kabilang side. So, you end up with this, no? With this term. Tapos yung n.c, okay? Ito yung n.c, tapos ang delta T nito ay 340 Kelvin minus 300 Kelvin. So you can calculate n.c. So n.c is equal to 50 divided by 40. And then, tama, 50 divided by 40. So that's 5 over 4. Ano? 5 over 4. So ang unit nito ay mole per second. Okay, so with this, we can now calculate the work loss. No? Ang formula lang naman natin ng W loss ay multiply lang natin yung T surrounding, multiply natin yung SG. So W loss, so ang T surrounding natin, so halimbawa, pwedeng dito muna ng stream. Ano? Ang SG natin dito ay CP, LN, T final, minus T initial. Ganun lang naman yun. No? So we're going to do this for both of the stream. Ano? Both sa hot at saka sa cold. So halimbawa, sa hot muna. So sa hot, ang temperature nun, ang surrounding temperature niya ay 300 Kelvin din. Okay? Tapos ang CP natin ay 7.5 R. R is 8.314 diba, joules per mole per Kelvin. Tapos times 1 mole per second. Ano? Okay? So, kita nyo ito, magka-cancel out yung mole, magka-cancel out yung Kelvin. So, actually, ang makakalculate natin dito is W dot loss. Yung rate ng, ng work. So, CP, LN, tapos ang final temperature ng hot natin ay 350 K. Dapat Kelvin, ano? Tapos divided by 400 Kelvin. Okay? Yun doon naman sa sa cold stream. So ganun din we have 300, nililitan ko lang dito ilalagay yun para magkasya. Times 7 halves times 8.314. Okay? Times 5 over 4. Okay, this is moles per second. Tapos LN. Ang final temperature natin sa cold ay 340. Tapos ang initial temperature natin ay 300. So, just try to input this in your calculator. Tingnan nyo kung ang makukuha nyo ay, this is co-current. So, dapat ang makuha nyo is 200.1. W loss should be equal to 200.1. So, ang unit natin dito ay joules per second. Try it. 300 times 7 divided by 2 times 8.314 times LN 350 divided by 100 times 7 divided by 2 times 8.314 times LN we have 350 divided by 100 plus 300 times 7 divided by 2 times 8.314 times 5 divided by 4 times 7 340 divided by 3. 200.1. Ano? Okay. So this would be the last video for chapter 5. So in the next video, I'm going to discuss some problems and some topics from chapter 6. So in the next video, you need the you need the steam table in the next exercise. So for now, see you in the next video.